Hello folks. In this video, I'm going to introduce the idea of electric potentials. Um, and it's a new tool. And the reason we introduce it, let me try to first motivate why we're introducing this new tool. So very often we are confronted with a scenario or a problem where we have all these different charges. We know the location of all these different charges, and we want to know how, if I introduce another charge into this system of charges, how would that new charge then move in the presence of all the other charges. Now, we already have the tools to calculate this, but the idea of introducing electric potential is going to help us organize our calculation and help us uh, calculate more efficiently. So, for example, let's take a common example that we see. Suppose there are these electrodes that I'm going to show you in this figure over here. There are these electrodes, they're in solution. And just for simplicity, let us forget about everything else, and maybe there's just one positively charged sodium ion right in the middle of these electrodes. And so you have the anode and the cathode. And so now that you know that these are all charged, somehow the sodium ion is going to interact with them and it's going to start moving. And we want to figure out how this moves. That is, what are the forces that act on the sodium ion, or maybe what is the energy of the sodium ion. And that's going to help us figure out the motion of the sodium ion. So the standard strategy is to figure out how each of this charge, say this positive charge that's right here, how does it interact with the sodium ion. So we will calculate that, maybe the force or the energy, then calculate for the next charge, how does this interact with the sodium ion, and then similarly with the next one and the next one. And so you have all these many charges, and you need to figure this out and figure out the interactions of all these different charges in order to answer the question, how does the sodium ion end up moving? Now suppose I have the same system, so they have the same arrangement of charges over here, except this time I'm looking at how the motion of a chloride ion is going to be. Want to figure out the motion of a chloride ion, and maybe it's not at the same position as the sodium ion. So if I look at the figure, maybe it's up there instead, and so now I need to figure out the new positions each time and how each of these charges then interacts with the chloride ion. Okay, so that means I have to redo all the steps of this calculation again. Okay, so the idea of introducing electric potential and electric fields, which we will do later on, is to help make these calculations, organize our calculations, and help make it more efficient. Okay, so that's one of the reasons why we introduce potentials and fields. So because we don't then need to talk about a particular sodium ion or a particular chloride ion, we can just do this calculation once and for all, and then when I need to answer how the sodium ion moves or how the chloride ion moves, I can just do a simple calculation to figure that out. I'll explain that in more detail with some example. So before that, let's first introduce the idea of the electric potential. So we already know that the electric energy is given by this form. So if I have two charges with charge Q1 and Q2, and they are separated by a distance which I denote by R, then the amount of electric energy between them is given by Kc, the constant, Q1, Q2 by R, and this is a quantity that is energy, so it's measured in joules. Right? So instead, now let's talk about an electric potential. Okay? The electric potential, on the other hand, is defined only for a single charge. Okay, so we denote it by capital V. And so for a single charge, I define the electric potential, or a single point charge, I define the electric potential to be, say, the same Coulomb constant, Kc, multiplied by the charge Q1 and divided by R. r represents the distance from some point in space. Okay, so note the slight difference in the use of r. Over here, r we said was just the distance between two charges. Over here, r just denotes some space point that you're interested in, and you want to know what the potential is at a point. Okay, so VQ1 is in fact going to be, we refer to it as a scalar field. And we'll understand what exactly we mean by scalar field uh, later on in class. But for the time being, let's compare our two definitions. So we said electric energy is defined this way and is measured in joules. Electric potential is now, if you do a bit of dimensional analysis, you will see it's defined in units of joules per coulomb, which is volts, right? So this is the same volts that you see on your car battery or on a simple AA battery. Okay, so the AA battery has 1.5 volts, so that's the same voltage volts that you see, same units that you see on a battery. All right, so so what's the idea? The idea is that if I wanted to figure out the energy, so if I wanted to figure out the energy for the sodium ion or for the chloride ion, I just simply need to calculate the potential at all points in space and time only once. And then if I wanted to find the energy for the sodium ion, then I simply multiply the potential with the charge of the other particle, right? So the potential at the the location of the sodium ion multiplied by the charge of the sodium ion. Similarly, if I have the chloride ion, I look at what the potential is at the location of the chloride ion and then multiply the charge of the chloride ion with the potential to get the energy. Okay. So given any charged particle or even a system of charged particles, all I need to do is to calculate the electric potential once and for all points in space and time. Okay. Once I do that, then for any other charge that I introduce to the system, the electric energy or the electric interaction is simply given by the electric potential at the point where I introduce the second charge Q2 and multiplied by the charge of the second charge. Okay. So let's make this a little more concrete with an example. Suppose I have a single positive charge sitting right at the origin over here. Now, this choice of origin is kind of arbitrary. You can put the origin anywhere. It's just very convenient to place it exactly where the charge you're interested in, or the electric. If I want to calculate the electric potential of a particular charge, then it's best to place the origin at that point. Okay. Then what I need to do is to make a map, right? I need to make a map of the potential at all points on this, say, XY coordinate system. In principle, there's also a z-axis, but we won't concern ourselves too much with a third coordinate. So how do I make a map? All I'm doing is I'm going to map out the value of the potential at every point in this grid. Okay, so for example, I've already written this out here. At this point, which is 3 units away from the charge, the potential is simply given by Kc q over 3. So q being the charge of this charge over here. So this is a plus q. And similarly, if I am 3 units from here, then it's again Kc q over 3. But what about if I want to figure out the potential at this point? Well, I need to know the distance from this point, right? And in a coordinate system like this is simply, that distance is simply given by 1, 2, 3, 4 units for the x-axis and 1, 2, 3 units for the y-axis. So therefore, from Pythagoras' theorem, that corresponds to, so let me just write this out as 3, and this as 4. So then Pythagoras' theorem is basically telling me that that distance is square root of 4 squared plus 3 squared, which is 5, right? So this is 5 units away. So the potential at that point is simply given by kcq over the distance, which is 5, right? And similarly, I'll do this for all points. So for example, this point over here will then be kcq over 2 because I'm 2 units away, and this is going to be kcq over 1, and I do this for all points. Okay, and so I've made a map, right? In the next video, I will show you a better way of representing the map, but what we're going to be talking about is, now that I've got a grid that has all the points that where I've mapped out the values of the potential at all points. The one way of representing that a little better. So let me redraw this figure. So again, I have this plus q, and let me use the example of kcq over 2, and this is kcq over 2, and I'm not filling out the rest, but somewhere over here, roughly speaking, is the distance is also 2, and so the value of the potential is also kcq over 2, and same over here and here and here and here and here and here and here. And so a nice way of representing all of this is to try and draw a line that connects all the points on this grid where the value of the potential is the same. Okay, so this is referred to as an equipotential line. That is the value of the potential along this line is the same, and in this example it's just kcq over 2. And in fact, I've only drawn this for the positive quadrant, but you can continue drawing this for the whole quadrant. So this is in fact just going to be a nice round circle. If you do the calculation, you will see that this is just a nice round circle. Okay, so that's one equipotential line. But I can do this now I can repeat this process for not just kcq over 2, but other values of the potential. So I could do it for kcq over 1, so something like that, right? And so now I'm basically trying to make a map of all these. I'm representing the potential that this single charge at the center created in terms of these equipotential lines. So this is a representation that we will use in class, and I will show you nicer simulations of these potentials, and we will practice them more in class.